Okay, so hello everybody. We're delighted to have today Joshua Zahl from the Chern Institute of Mathematics at Nankai University, who will deliver his second Nirenberg lecture.
Thank you. So I'm going to talk today about some joint work by Hong Wang and myself. And this is building towards the proof of the Kakeya set conjecture in R3. So Hong and I proved this somewhat recently, and this most recent paper of ours built on a previous result from 2002, where we solved a special case of the Kakeya set conjecture that we call the sticky Kakeya conjecture, again, in 3 dimensions. And I'm going to talk today about what that conjecture says and how we proved it. And then Hong's talk on Thursday will build off that. So very roughly, our proof, our full resolution of the Kakeya conjecture takes a Bezukovich set and splits very roughly into the case where that set is sticky versus non-sticky. And the arguments that are employed in these 2 different settings look rather different. So these are somewhat disjoint pieces of the argument. So before we get started, I want a little bit of history. So the history of the Kakeya conjecture goes back at least to the 1970s with work of Davies and Cordoba. But in 1995, Wolff proved that every Bezukovich set in R3 has Hausdorff dimension at least 5 halves. His result is more general than that, but in R3, this is what he showed. So I'll just say HDIM is Hausdorff dimension, at least 5 halves. And as we'll see in a few minutes, this is a very natural barrier for the Kakeya set conjecture in R3. And so it was quite striking when a few years later, Katz, Waba, and Tao so this was in 2000, obtained a slight improvement. So 5 halves plus some small but in theory explicit epsilon naught, not for the Hausdorff dimension of a Kakeya set in R3, but the upper Minkowski dimension. So they showed that every Bezukovich set in R3 has upper Minkowski dimension, at least 5 halves plus a small but in theory explicit epsilon naught. And the way they did this is they analyzed the structure of a hypothetical Bezukovich set in R3 that had upper Minkowski dimension exactly 5 halves. What does it mean to have upper Minkowski dimension exactly 5 halves? It means you have this Bezukovich set. This is some compact set K in R3. And for every positive delta, you could consider the delta thickening of this set. And now this delta thickening, not only does it contain a unit line segment in every direction, but it contains a delta tube in every direction. And in particular, you can extract a set of roughly delta to the minus 2 tubes pointing in delta separated directions. And the volume of the union of these tubes will be roughly delta to the 1/2, right? So delta to the 3 minus 5 halves, which is 1/2. And if you thicken this union of tubes, take its row neighborhood for every possible row, that will have volume roughly rho to the 1/2, right? So if the volume was substantially larger than rho to the 1/2 for some sequence of rows tending to 0, then that would give you an upper Minkowski dimension bigger than 5 halves, and we're imagining that that's not the case. So they analyzed the structure of what such a family of tubes would look like, and they showed that such a family of tubes would have to have 3 structural properties, which they gave the names planiness, graininess, and stickiness. And eventually, with a lot of work, they were able to arrive at a contradiction using the fact that the lines in the Kakeya set point in different directions. They could apply some sums differences from additive combinatorics. Get a contradiction. When you make this quantitative, you do a little bit better than 5 halves. So after that, Katz and Tao had this program for trying to solve the Kakeya set conjecture in R3. And step one of the program was to say, imagine we have a counterexample to the Kakeya set conjecture, some Kakeya set, some Bezukovich set of dimensions strictly less than 3. Step one, try to show that it has to have these properties of planiness, graininess, and stickiness. Okay, they weren't exactly sure how to do that, but imagine you could do that. And step two, after a lot of work, obtain some, as a conclusion of this, certain structural properties of this Bezukovich set and eventually arrive at a contradiction. They had some idea maybe of how to go about doing that. But this first step of how to show that a counterexample to the Kakeya set conjecture would have these 3 properties, it wasn't entirely clear how to do that. So I haven't told you what any of these 3 properties mean, planiness, graininess, stickiness. I'll get to that. Planiness and graininess, it turns out, subsequent results showed that if you had a counterexample to the Kakeya set conjecture in R3, it would have to have these 2 properties of planiness and graininess. It wasn't clear how to establish stickiness. So after a while, Katz and Tao decided they weren't interested in this question anymore. They put it aside. And in 2014, Terry Tao gave a talk at IPAM where he outlined this program that he and NetsCats had. And they said, we're done with this. We're going to explain it to the world in case anyone else wants to pick it up. So Hong and I were interested. And we also didn't know how to show that a counterexample to the Kakeya set conjecture would have to have this property we call stickiness. But we decided to sort of work backwards and say, let's restrict ourselves to those sets that have this property that we call stickiness. I'll tell you what it is in a moment. And let's show that sets with this property have to have full dimension. So this is what we did. And then more recently, we were able to, in some sense, consider sets that don't have this property called stickiness and handle them as well. So let's give some definitions. And I'm going to start with a definition I didn't write as such, but I already introduced yesterday. So sometimes I'll write tubes or delta tubes. Delta is always implicit in the background. So I'll say, we say a set of delta tubes satisfies the Wolf axioms and I'll maybe add some additional quantifiers here in just a moment, but for now, I'll say we say a set of delta tubes satisfies the Wolf axioms if for every convex set, let's say we're in R3, doesn't actually matter right now, if for every, let's say, delta tubes, let's say in R3, although this definition makes sense in higher dimensions as well, if for every convex set, W, the number of tubes contained in W, is at most, let's say up to a constant, the volume of W divided by delta squared. And why do I pick delta squared? Well, that's the volume of a tube in R3. In higher dimensions, you can imagine changing this in an appropriate way. So this is the definition I'm going to use. There are some closely related definitions that Hong might introduce in her talk on Thursday. So Hong might say that we say a set of delta tubes satisfies the the Katz tau convex Wolf axioms. And so why do I add these quantifiers? So first of all, convex Wolf axioms is saying that I am forbidding concentration inside of convex sets. You could imagine more general classes of sets in which I forbid concentration. And Katz tau is a type of non-concentration condition, which roughly says the number of tubes that can concentrate inside of a convex set is at most the volume of the convex set divided by the volume of a tube. There'll be other settings where we care about slightly different non-concentration conditions. For example, the left-hand side might be controlled by the volume of my convex set times the total number of tubes. That's a slightly different type of condition. But the only thing I'm going to talk about today is this condition here. And in particular, if you have delta tubes in R3 pointing in delta separated directions, they satisfy this property. And we already discussed that yesterday.
Are there
What's that?
Are the delta tubes of length 1?
Yeah, so in everything I do, these delta tubes are going to have length 1 and thickness delta. That's what it means to be a delta tube for us. Great. And the volume in R3 is delta squared up to a constant, which I don't care about. And we could weaken this losing a constant, maybe even losing a log factor. I'm not going to be too worried about that today. What's that?
The confidence universal?
Well, if we want to be more concrete, we could say it satisfies these axioms with error capital C, if this holds with a C here. And we could consider various values of C. We're typically going to be interested in inequalities of this form where we're losing some subpolynomial loss. But that distinction I'm not going to care about too much today. Pretty much every statement I'm going to say here is a slight lie, and the reality is going to involve several layers of nested quantifiers that I'm going to avoid getting into. Okay, what did I want to say? So there's several different definitions of what it means for a set of tubes to be sticky, but the one that's cleanest for us today is the following. So I'll say, we say a set of delta tubes T is sticky if, so first of all, at least for today, I'm going to say that the number of tubes is roughly delta to the minus 2. In particular, observe, if you have a set of tubes, everything takes place inside of, let's say, the unit ball. If you have a set of delta tubes which satisfy the convex Wolff axioms, everything's inside the unit ball. If I let W be the unit ball, that has area roughly 1, that's telling me the cardinality of my set of tubes is at most delta to the minus 2, up to a constant. And so in order to be sticky, I'm going to require that the reverse equality roughly hold. So I have roughly delta to the minus 2 tubes. So this is true. And so that's item 1. And item 2, for every intermediate scale row, we can cover, or there exists a set of row tubes there exists a set of row tubes, let's call them T row, that covers T. What do I mean? But T row covers T. I mean, so T row is a set of row tubes, and if this covers T, then every delta tube inside of T is contained inside of at least one row tube in T row. I could ask that it be approximately 1, so contained in at least 1, at most 100, for example, that covers T. And T row satisfies the convex Wolff axioms, or the Wolff axioms. T row satisfies the Wolff axioms. Okay, and now of course that's a set of row tubes, so I'm dividing by rho squared here. And again, this definition could be weakened by inserting various constants here, etc., but I'm not going to focus on that. So what Hong and I proved in 2002, say this is Wang and myself, 2022 rather. And the formulation here is in a later paper. It says the following, so let T be a set of sticky delta tubes, or a sticky set. So then the volume is almost maximal. And this is the notation that I introduced yesterday. So for every epsilon, there exists some positive number c sub epsilon, so that the volume on the left-hand side is at least c sub epsilon times delta to the epsilon. Okay, so if you restrict attention to this particular subclass of the Kakeya problem, where you only have sticky tubes, then we get the desired volume bound. And in fact, we prove something a little bit stronger, which is more technical, and that slightly stronger statement is what we need to fully resolve the Kakeya set conjecture. And what we prove is, so I won't write it down precisely, but let's say you only want a bound of the form, a lower bound delta to the epsilon for some concrete but small epsilon, then certainly that is implied by this statement here. But if you're willing to weaken the conclusion in this way, you could also weaken the hypotheses. And so rather than requiring that the set of delta tubes be sticky in this very strong sense, you can slightly weaken the condition of them being sticky. And you can say for every row between delta and 1, you can weaken this notion of satisfying the convex-Wolf axioms and put in some delta to the minus a different epsilon. So delta to the minus eta there. So I won't focus on that at all today. It's already complicated enough. But all I'm saying is these hypotheses can be weakened at the cost of weakening the conclusion slightly. But that weakening of the conclusion is still sufficient for our purposes. Okay, so hopefully this statement makes sense. We're restricting to a special class of arrangements of tubes. And one way to think about stickiness, because it's a little hard to understand right now. So a conventional Kakeya set or a Bezukovich set, right? For each line, you have a unit line segment point. For each direction, you have a unit line segment pointing in that direction. You can think of this as a function from the space of directions. Maybe that's the sphere S2 to the set of lines, which is a certain Grassmannian. And one example of a sticky Kakeya set would be if this function is Lipschitz. So the function that assigns directions to lines, if that is Lipschitz, then you are definitely sticky. That's a very strong condition. If you have a Lipschitz function assigning directions to lines, it's actually not too hard to prove the Kakeya set conjecture in that setting. If you have a Lipschitz function, then you could look at its graph, and the dimension of its graph will be the same as the dimension of the domain if you're Lipschitz. And that's really the condition we need. In order to be sticky, the dimension of the graph has to be the same as the dimension of the domain. What notion of dimension? It turns out a Swan dimension is the right notion for this definition here. So that's one way of thinking about what it means to be sticky. Okay, but this is the precise statement, which is useful for us. Now, one of the reasons that this is a challenging theorem to prove, and one of the reasons, in fact, that doing any better than Wolf is rather hard, is that there is almost a counterexample to this statement, and I want to tell you what that is. This counterexample was first written down by Katz, Wabe, and Tao in their paper, and they also had to grapple with this. It's not literally a counterexample. We like to call it a near miss. It is a object which satisfies most of the hypotheses of the Kakeya set conjecture, but for which the conclusion fails quite dramatically. And this near miss is called the Heisenberg group example. And it's very explicit. I'm going to use Blackboard bold H. And it is not a subset of R3, it's a subset of C3. It's the set of triples of the form X, Y, Z in C3, so that the imaginary part of Z equals the imaginary part of X, Y bar. So very, very concrete subset of C3. What is the dimension of this set? Well, okay, if we use the Euclidean metric on C3, then C3 has Hausdorff dimension 6. And this set here has Hausdorff dimension 5. In fact, if we associate C3 with R6, then this is just a quadratic hypersurface in R6. So it's perfectly well behaved. And we say, okay, well, C3 has Hausdorff dimension 6, R3 has Hausdorff dimension 3. So if we're going to create an analogy between these two, we should divide by 2 the dimension of a subset of C3 to think about what its real dimension would be in this analogous setting. And so this set is the analog of a 5/2 dimensional set. And it contains a lot of complex lines. So I can say if I have real numbers A, B, C, D, then I'm going to define a certain line associated to this 4-tuple. This is a complex line. And what is it? Well, I'm going to give it to you in point vector notation. And so the first coordinate will be 0. And maybe I'll write this as C plus DI, and make sure I don't screw this up. I'll check my notes. The last coordinate, let's call this A. So this is the point. And then the vector is 1. Sorry, don't screw this up. It should be B, C minus DI. T, as T ranges over C. Okay, so hopefully we agree this is a complex line in C3, point vector notation. And I claim that for every 4-tuple of real numbers, A, B, C, D, this line is contained in H. how do we verify that? I have to ensure that I satisfy this equation, and maybe I won't do all that for you, but I'll just say to verify that the imaginary part of the last coordinate, which is A is a real number, so the imaginary part is nothing. C plus di, ct minus dit equals the imaginary part of what is x, so that is t times c plus di and plus bt bar. Okay, so we can compute this in a fairly straightforward fashion and realize that for every complex number t, we have equality here. And what this tells us is that these complex lines are all contained in H. So that's kind of interesting. We have a 4 real parameter family of complex lines contained inside of this set. If we're going with this analogy that we should divide the dimension of everything by 2 in going from C3 to R3, then this looks a lot like a 2 dimensional family of lines contained in my 5/2 dimensional set. If I were to take the delta thickening of everything here and also intersect with the unit ball to make it closed, or make it compact, let's say, then it looks an awful lot like I have delta to the minus 2 lines whose union is contained in a set of dimension 5/2, or the delta thickening of a set of dimension 5/2. And you can verify that this set of lines satisfies the analog of the convex Wolf axioms. They do not concentrate inside of convex sets. So that's rather interesting, right? If you were to very, very slightly weaken the definition of what it means to satisfy the Wolf axioms and what the Kakeya set conjecture for sticky Kakeya sets says, to forget about the underlying field and allow the complex numbers as an allowable field, then the conjecture becomes false. So the proof needs to do something which distinguishes the complex numbers from the real numbers. And at every single step in the proof, you should ask yourself, can we see the difference between the real numbers and the complex numbers at this step in the proof? And there'll be one key step where you can. Okay. So now I want to start to launch into the proof and get as far as I can of this statement here. So I'll pause for a moment to ask if there's any questions. Hopefully the statement makes sense. At least one difficulty is apparent, the existence of this near miss, this almost counterexample. And we have to somehow distinguish this near miss from the reality. Okay, so here's how we're going to do it. So I'm going to imagine that this theorem is false, and I would like to try to understand of all the counterexamples to this theorem, which one is the worst counterexample, the most extreme counterexample to this theorem. And so what I'm going to do is I'm going to define sigma to be the supremum over all, let's call it all T, the following property. There exists a sticky Kakeya set T with the union having volume less than delta to the sigma. If I can prove that sigma is 0, then I'm very happy. I've proved this theorem here. Right? Because that 1 is sigma to the power of 0. And there's some quantifiers lurking under the surface here. Maybe I need a whole sequence of deltas tending to 0, this property. But let's imagine, at least for the moment, that this is my definition of sigma. So sigma is the worst possible exponent measuring the worst possible failure of this theorem. I want to prove sigma is 0. And so let's assume for the rest of today that sigma is strictly positive. We want to arrive at a contradiction. And I'm going to imagine that there exists a set of tubes that actually realizes this. So it's not clear that the supremum is realized, but that's the least of the lies I'm telling you. So T is a set of delta tubes, sticky. Maybe I may forget to say sticky, but everything is sticky. Delta tubes. Let's just say we have equality. Again, I'm willing to hemorrhage delta to the epsilon factors everywhere. So what does it mean if the union of these tubes has volume delta to the sigma? Well, what this tells us is that roughly delta to the minus sigma tubes pass through each point in this union, right? If you add up the sum of the volumes of all these tubes, you get roughly 1, because there's roughly delta to the minus 2 of these tubes. They each have volume delta squared. So if the sum of the volumes is 1, but the volume of the union is delta to the sigma, which is substantially smaller than 1, okay, we expect about delta to the minus sigma tubes through each point. And I'm going to call this number mu sub t. So in general, if I have a set of tubes, mu sub t is the typical number of tubes through a typical point in the union. Okay, hopefully we are good so far.
Sorry, this will be T.
Whoops, sorry, that should be a t. Thank you. Yeah, sigma, thank you. Yeah. And so here's a crucial starting point, and this goes back to the ideas of Katz and Tau. Let's take such a set of tubes, T, and I want to consider what's happening at an intermediate scale rho. So I'm going to let rho be a number between delta and 1. Ultimately, I'm going to consider many different scales rho, and I'm going to let T rho be a set of tubes that satisfies the convex Wolf or the Wolf axioms of the correct cardinality, which covers my set T. I know that such a set T rho exists by the property of stickiness. And it's not too hard to show that T rho is also sticky. That's a somewhat straightforward exercise. The stickiness of T enforces that same property for this thicker set T rho. And a second object is also sticky. So if I take a rho tube, T rho, inside of this family, then what I'm going to do is I'm going to look at this. So this is blackboard bold T, super T rho. And what does that mean? So here's my rho tube, T rho. And inside of this is a bunch of delta tubes. In fact, I know pretty much exactly how many delta tubes. It's roughly the total number of delta tubes, which is delta to the minus 2, divided by the number of rho tubes, which is rho to the minus 2. So there's roughly rho over delta squared, delta tubes inside of this rho tube. And I'm going to rescale this so that now this is more or less the unit ball. Right, so I'm doing an anisotropic rescaling by a factor of 1 over rho in these two directions. And now I have delta over rho tubes inside. And it's not too hard to show that this new family of delta over rho tubes will also be sticky. Okay, so this is a nice property of stickiness, and the definition of stickiness was tuned to make this fact true. You cover your delta tubes by rho tubes. The rho tubes are sticky. The rescaled delta tubes inside of the rho tubes are sticky. And that's kind of interesting. So I picked my set of delta tubes to be a worst possible counterexample to the theorem we'd like to prove. T rho is another sticky set of tubes. I don't know if it's a worst possible counterexample, but it can't be any worse than the worst possible counterexample. So I have a reasonably good lower bound on the volume of the union of the T rho, or equivalently, I have an upper bound on the multiplicity, the intersection multiplicity of the T rho. I know that it's no worse than rho to the minus sigma. Right? So what I'm going to write is mu sub T rho is less than or equal to rho to the minus sigma. Because this is how more or less how I defined sigma. It is the worst possible exponent for the amount of overlap of a sticky collection of tubes. And these guys are also sticky. So what I also know is that mu of T super T rho is at most delta over rho to the minus sigma, because these guys are sticky. And this is true for every T rho. And this is kind of interesting. So what do I know? I know that the intersection multiplicity of these tubes is roughly delta to the minus sigma. This is because my original set T was chosen to be a worst possible counterexample to my theorem. Now, what is mu sub T? It's the typical number of delta tubes that pass through each point in my union of tubes. And now what I'm doing is I'm taking my union of tubes and I'm covering it by row tubes. And what I can ask now is how many delta tubes pass through a typical point in this union? And one way to bound that from above is I can ask, well, how many row tubes pass through this point? And then for each one of these row tubes, how many delta tubes pass through that particular point, restricted to that particular row tube? And this gives me an upper bound. So this is at most mu sub T row, mu sub T, T row. And what is that? Well, that's roughly rho to the minus sigma times delta over rho to the minus sigma. This is delta to the minus sigma, and I have equality. So what this tells me is that every one of these inequalities is roughly an equality, and this gives me a huge amount of structural information about my worst case counterexample to the sticky Kakeya conjecture. What it's saying is each one of these sets, or it's saying that T row is not just a sticky Kakeya set, it is also a worst possible example, a worst possible counterexample to this sticky Kakeya theorem. These rescaled guys, each one of them is a worst possible counterexample to the sticky Kakeya theorem. And it's also saying, maybe we'll draw a picture here, take any point in the original union of tubes, look at every single row tube which contains that point. For every such row tube, there's got to be delta tubes inside of it, which also hit this point. So if a row tube passes through a point, the delta tubes inside of that row tube also pass through the point. And this is very powerful because what it tells us is if we have some information about the set of delta tubes passing through this point, that also tells us information about the row tubes passing through that point. And so we can bubble up information from finer scales to coarser scales. And this is a useful thing to do. Okay, so this is sort of the starting point for the kinds of, you could call it coarse self-similarity that these extremal counterexamples to the sticky Kakeya conjecture have to have. And this allows us to develop a lot of structural information about what these sets look like. So now I want to spend a little while talking about this structural information. What can we say about what a hypothetical worst case counterexample to the sticky Kakeya conjecture would look like? We're going to get more and more structural information. And eventually, we're going to come up with a statement which is allowed to hold over the complex numbers, because everything I've said so far is true for this Heisenberg group counterexample, but isn't allowed to hold over the real numbers. And so we should keep an eye out for that key moment where we distinguish R from C. Okay, I'll pause for a moment. Any questions so far? Okay. Let's see. Okay, well, the Heisenberg example, the fact that it exists will be very important for us. Its precise form will not be so important, so I can safely erase it. The first property I want is this property that I called planiness, and I didn't tell you what it is. But roughly speaking, what planiness says is for each point, when I say each point in my Kakeya set, really what I mean is each point in my union of tubes. You could look at all the delta tubes which pass through that point, and planiness is saying that they're all coplanar. And it's not really obvious that such a thing should be true. In general, you could imagine the tubes pointing in any direction whatsoever. But if you have a worst case counterexample to the sticky Kakeya conjecture, then all those tubes have to be coplanar. And here's why this is true. So there's the multilinear Kakeya theorem, which is proved by Bennett, Carberry, and Tao. And in R3, it's the trilinear Kakeya theorem. So I'm going to call this the Bennett, Carberry, Tao multilinear Kakeya theorem. And what they prove is more powerful and more general than what I'm about to say. I'm just going to tell you a special case. But a consequence, a special case of their theorem is the following. So I can say let T be a set of delta to the minus 2 delta tubes in R3. And suppose that for a typical point in the union of these tubes and a typical triple of tubes passing through X, so T1, T2, T3, which all contain X, right? So I take a point in my union of tubes. I'm going to look at a typical triple of tubes, which contain that point. And every tube has a direction. And so now if I take a typical triple of tubes, I have a typical triple of unit vectors giving their direction. And I can ask how linearly independent are they? I can take the volume of the parallel pipe that's spanned by those three, or the wedge, if you will. So I'm going to look at the wedge. So V1 is the direction of the tube T1. Wedge V2 is the direction of the tube T2. Wedge V3 is the direction of the tube V3, and the volume of that. So if these tubes are pointing quantitatively linearly independent directions, this wedge has size roughly 1. If they're all coplanar, the wedge has size 0, and there's intermediate behavior in between. So if this wedge has size roughly 1, which could happen for certain arrangements of tubes, if this happens, then the volume of the union of the tubes is roughly 1. So they prove something much more general. But what they're saying is if you're looking for a counterexample to the Kakeya conjecture, you're not going to find it amongst families of tubes with the property that look at a typical point in the union, look at a typical triple of tubes passing through that point. They point in 3 linearly independent directions on average. If this is happening, this is not how you get a counterexample to Kakeya. So what's the contrapositive of this statement? Imagine the sticky Kakeya conjecture is false. I have a counterexample, maybe an extremal counterexample, and I look at a typical point in this union, and I look at a typical triple of tubes passing through that point. The contrapositive of this statement is that the wedge is very small. It has size much, much smaller than 1. And if I have 3 vectors in R3 and their wedge has size much, much smaller than 1, what does it mean? It means they're coplanar, at least roughly. So there's quantifiers looking in the background, which I'm not telling you. But the conclusion we care about is if T, oh, I didn't give this a name. T is a sticky set of delta tubes. Maybe I'm going to call this an extremal counterexample. So an extremal counterexample is a counterexample where this is as bad as it can possibly be. Right? It realizes or almost realizes this supremum. It'll be a bit vague between realizes and almost realizes. So if Blackboard bold T is an extremal counterexample to that statement, extremal counterexample, well, then for a typical point, for a typical triple of tubes passing through that point, they're almost coplanar. But now fix your favorite point. If it's the case that most triples of tubes passing through that point are coplanar, then by pigeonholing, you can quickly convince yourself that all of the, or almost all of the tubes passing through that point need to be close to a common plane, right? I mean, if those typical triple is coplanar, well, take 2 of those guys, they're going to span a plane. The third guy has to be close to that plane. That's true for many, many choices of third guy. You can quickly pigeonhole yourself and convince yourself that what this means is, I'll say for every is a slight lie, X in the union of the tubes, there is a 2-plane, so that all the tubes passing through this point make small angle with the 2-plane. And another way of thinking about it, instead of specifying a 2-plane, I can tell you the normal direction to that 2-plane. We're in R3, right? So that most of the tubes point in a direction that's almost orthogonal to that normal direction. That's a slightly cleaner way of saying you're close to a 2-plane. So for every X in the union, whoops, there's a vector, let's call it V of X. So for every X in this union, there is a vector V of X. This is in S2, right? We're in R3, so unit vectors in R3, such that the dot product, the direction of T dotted with V of X, is small. How small? Well, much smaller than 1. And I can tell you exactly how small in a moment for all. And again, all is in quotes. T and T containing X. So all is a bit of a lie, right? But what it's telling you is for every point in this union of tubes, there's a two-plane, it has a normal direction. All the tubes, most of the tubes passing through this point make small angle with this two-plane, and thus a typical triple has small wedge. Equivalently, it has small dot with this vector v. So hopefully this is believable. And this statement of Bennett-Carburet-Tau, it's in fact quantitative. It tells you how the volume of the union depends on the size of this typical wedge. And when you do this precisely, you get something. And what you get is something like, if you're a bit sloppy, something like delta to the sigma over 2. Maybe if you work really hard, you can do a bit better and get delta to the sigma, but we don't care. Sigma is some strictly positive number, so we are making somewhat small angle with this vector v. Okay, so what this is telling you is for every point in your union of tubes, there is a two-plane, so the most or all of the tubes passing through this point make somewhat small angle with this two-plane. Now, we'd like to show that sigma is 0. You can imagine, for counterexample, that sigma is 0.01. And delta to the 0.01 over 2, that is substantially smaller than 1, but it's still a somewhat large angle. We don't have a ton of control over what's going on. But here's where we make absolutely critical use of the fact that if you look at the row tubes passing through this point, every row tube that contains this point in my original union of tubes, there's also a delta tube contained inside the row tube, which passes through this point. So now what I'm going to do is I'm going to consider what happens when rho is delta to the sigma over 2. And what the heck is going on? So I have this yellow point. I know that there is a vector v, so that every delta tube passing through this point is somewhat orthogonal to that vector v. How orthogonal? It makes angle at most delta to the sigma over 2 with the orthogonal plane. But all of these much fatter tubes passing through this point need to contain a delta tube which has that property. And if you think through what this means, it means that each one of these delta to the sigma over 2 tubes also needs to make angle at most delta to the sigma over 2 with that vector v. And that seems like a much stronger statement, right? If I rescale things, I'm going to rename delta. I'm going to forget my original union of delta tubes, and I'm going to replace them with their delta to the sigma over 2 thickening. I have a new extremal Kakeya set. I'm starting from scratch. But now there's a much stronger property. For every point x in the union, there's a vector v such that now this is at most delta. And why is it at most delta? Because what I used to call delta to the sigma over 2, I've renamed to be delta. So this kind of rescaling or coarsening I'm going to do a lot. And it upgrades weak structural properties to strong structural properties. Okay, so this is a starting point. And so this is what planiness tells me. But I can do a lot more. I can ask, how does this vector v of x change as I move my point x around? And let's say I take two different points, x and x prime, which have a certain distance, substantially less than 1. And I want to understand how these things differ. Well, I can take two rather fat tubes, whose intersection contains x and contains x prime. And this property that if a tube passes through a point, then I have control between this angle. Well, if I do this at a much coarser scale, this is actually going to establish that this function v of x is Lipschitz. So there's a bit of an argument there, but it's a very similar argument to what I just told you about here. So this function is Lipschitz. Okay, so I'm glossing over some details of how to achieve that, but I claim it's nothing that different than just taking a point here and taking a second point here and asking how much can these two vectors differ? Well, both of these vectors have to be orthogonal to this guy and to this guy, and that's the same pair of tubes, and orthogonal up to what resolution? Up to the resolution of the thickness of the tube. And this is what this establishes Lipschitzness. Okay. Everything I've said so far is also true in this Heisenberg group counterexample. So we have not distinguished a Heisenberg group counterexample. It has a Lipschitz plane map. Unfortunately, I'm going to have to speed up a little bit, which is unfortunate, but okay. Next, what I want to do is establish a property called graininess. And what this tells me is I want to look at what's happening inside of a ball of radius root delta. So I'm going to take a delta tube, and I'm going to look at a ball of radius delta to the 1/2. And what I should expect is for lots of other delta tubes to be hitting this delta tube here, all along this delta tube. But I'm only going to look at what's happening inside of a ball of radius delta to the 1/2. So what's going on? I'm going to call this the stem tube, and all the tubes which hit it, I'm going to call the hairbrush. And there's this Lipschitz plane map, V of x, so that all the tubes passing through each one of these points are orthogonal, so they're in a two-plane whose normal direction is V of x. And that two-plane changes in some Lipschitz way. So if I move distance root delta, it only changes by about root delta. So at resolution root delta, it hasn't changed at all inside of this ball radius delta to the 1/2. And so all of these tubes hitting this piece of my stem, they're all roughly coplanar inside of this ball of radius delta to the 1/2. So inside of this ball, this looks an awful lot like a two-dimensional Kakeya problem. I have a stem tube, I have a bunch of other tubes which hit it. Everything's inside of ostensibly a ball of radius delta to the 1/2, but really, it's, if I draw this as a square, it's inside of a slab of width delta to the 1/2 and thickness delta. And this is a two-dimensional Kakeya problem. We understand the two-dimensional Kakeya problem very well. This goes back to Cordoba and before. And what I discover is that the union of the tubes which hit this stem more or less fill out this slab. So this is a delta times delta to the 1/2 times delta to the 1/2. I'm going to call objects of these dimensions grains. And if you look at the hairbrush of a tube, the set of tubes which hit my stem, inside of this region, you fill out an entire grain. So what I conclude is that my union of tubes, we conclude, can be written, or decomposed if we want, to a union, disjoint union, of these grains. And these are rectangular prisms of dimensions delta times delta to the 1/2 times delta to the 1/2. And how can I see that? Well, look inside of these balls of radius delta to the 1/2 and just look at all the tubes which hit one stem, and they fill out these grains. So this is a very different kind of structure from my original union of tubes, but it also exists inside of my extremal counterexample to the Kakeya conjecture. And now what I want to do is I want to go back to looking inside of a ball of radius delta to the 1/2. It's going to be a little bit easier to draw if I draw it as a cube of radius of side length delta to the 1/2. The distinction's not so unlike yesterday's talk, where the distinction between a square and a disk was very important. And what I'm about to say, the distinction between a cube and a ball is just which one's easier to draw. So let's draw a cube of side length delta to the 1/2. And what I conclude is that the intersection of my Kakeya set, by which I mean my union of tubes, with this cube, is going to look like a bunch of parallel grains. So these are these slabs of dimensions delta by root delta by root delta. And why are they parallel? Well, their normal direction is given by this function v of x, which is Lipschitz. The normal direction only makes sense up to resolution, the ratio of this guy divided by this guy. So that's resolution delta to the 1/2. And this Lipschitz function can only change by about delta to the 1/2 inside of this cube. So these guys are parallel, as best I can tell. And so now I know something about the structural information of what a counterexample to the sticky Kakeya set conjecture looks like. If I look at what's happening inside of a cube of side length delta to the 1/2, it looks like a union of these parallel slabs. And this is, in some sense, a one-dimensional object, by which I mean I can tell you everything you need to know about this object by just looking at where these intercepts are. And so what does this look like? Well, if I were to say intersect with this line here, I get a bunch of intervals of length delta. And one could ask, how many do I have? And I could ask, how are they arranged? And it's not too hard to do a count of how many you have. So the side length is delta to the 1/2. And we're imagining our counterexample to this Kakeya conjecture has dimension 3 minus sigma. And so the number of them is going to be this to the sigma minus 1. And that's a computation you can do without too much trouble. So that's how many of these slabs you have. And then you could ask, how are they arranged? And that takes a little bit more work. But they're arranged a little bit like a Cantor set. You could say a middle thirds Cantor set. It's not literally a middle thirds Cantor set, but it has a lot of the same self-similar properties that you might expect from a Cantor set. So what I mean by this is if I take a shorter interval and I ask how many of these are contained in that shorter interval, it is the length of the interval to that appropriate power. That's an upper bound. But I also have an almost matching lower bound. So this is, for those of you that know this keyword Alfors to be regular, this is sort of coarsely Alfors to be regular. So I have a lot of structural information. This thing looks something like a fractal set. That's not a well-defined term, but it looks in many ways like a Cantor set of an appropriate dimension. Okay, so now I have a fair bit of structural information, and I'd like to exploit this information at several different scales. So here's what I'm going to do. I'm going to take a delta tube in my set. I'm going to consider, actually I'm going to draw it vertically. I think that's a bit cleaner. And you know what? I'm even going to give myself a new board because I'm going to need some room. So this is sometimes called the global grain structure. It's a capital G. So I'm going to take a delta tube in my set. I'm going to consider the corresponding thickening at scale delta to the 1/2. And if I want, I can chop this into cubes. Okay, they're not literally cubes, but they're close enough to being cubes of side length delta to the 1/2. How many of them are there? Well, there's the reciprocal of delta to the 1/2. And each one of those cubes looks something like this. It's the intersection of this tube with my Kakeya set, with my union of delta tubes, is a bunch of cubes. And each one of these cubes is filled with a bunch of these parallel grains. So inside of each one of these cubes, those grains are parallel to each other. But as I move from cube to cube to cube, that parallel direction is twisting in some fashion. And how is it twisting? Well, it's twisting according to this function v of x that I might have erased. It's a Lipschitz function. Okay, so it looks kind of like this. And I can't really draw it twisting, but you'll have to use your imagination. And now what I'm going to do is I'm going to do an anisotropic rescaling by the reciprocal of delta to the 1/2 in these two directions. And so now I have a set which looks like this. It's more or less the unit ball. What used to be delta tubes inside of this root delta tube have gotten wider, and now they are themselves root delta tubes. And what used to be these little grains, which twisted as you went along, have now gotten much wider, right? Each one of these delta cubes is now an entire slab in my unit ball. And so what this means is if I take a slice, maybe this guy here corresponds now to a slice in the, let's say this is the z direction. And so this is a slice, which is maybe z equals z naught. That's a particular slice of my original picture. And what used to be these parallel grains inside of this cube have been expanded in these two directions. Let's take a new color. Maybe to try to keep it consistent, I'll draw these grains, all of them. Those are these grains, same grains. I've just drawn a different part of the same picture. And now these things look like, well, if I slice z equals z naught, these look like parallel lines. Not just lines, they have thickness delta to the 1/2. So this is kind of interesting. I have this root delta neighborhood of a tube, or a thick tube. Inside of it are delta tubes. I blow this thing up. Now I have these fatter tubes, which are delta to the 1/2 tubes. But that's the thinnest scale that exists at this point. So now everything is taking place at scale delta to the 1/2. And every time you take a z equals fixed slice and you look at how these tubes intersect that slice, they intersect in a union of these rectangular prisms. And what is the width of these? My picture is not exactly to scale, because the width of these guys is supposed to be delta to the 1/2. And then the length of these is 1. So that's what's going on now. I have a lot of structural information about what this union of tubes look like after I've rescaled. But this rescaled picture is, again, an extremal counterexample to the Kakeya set conjecture. So every structural thing I've said so far also applies to these. In particular, I again have this same kind of local grain occurring inside of this picture, right? So I have, let's do a renaming. I'm going to rename. Rho is delta to the 1/2. So now I have these rho tubes, and they cluster inside of these rho times root rho grains. But every fixed Z slice is also a union of rho times 1. I'm going to call these global grains. So I have these two complementary structures occurring inside of my set. And again, all of this is still happening in the Heisenberg group counterexample. We have not yet distinguished between the Heisenberg group counterexample and a genuine Kakeya set, but we're getting close. So there's one final thing I want to do, and I apologize for all of the steps involved, but it takes somehow, it's very subtle distinguishing R from C. You really have to know where to look. It's a bit of a walk, but we're getting there. So the last thing I want to do is I want to do one more zooming in and rescaling. And I want to take one of these global grains, and I want to consider a certain neighborhood of that grain. I want to zoom in on what it looks like. And so this thing actually has length 1 in the Z direction. It's very foreshortened, so I didn't draw it wonderfully. And it has width rho. And I'm going to consider its, maybe I'll do this in orange. It's rho to the 1/2 neighborhood horizontally, and it's rho to the 1/2 neighborhood vertically. And then it's full length. So this looks like a rectangular prism. It has length roughly 1. And it has, I don't think I like, let me just see how I spent a while drawing it and staring at it and trying to say, what's the cleanest way to draw this to make it look nice? Let me try it one more time to draw this. Maybe I'll start by drawing the front of it. Okay, so this is very much reaching the end of my drawing ability. So this is meant to be a rectangular prism of width rho to the 1/2, of length 1 and height rho to the 1/2. And what the heck is this thing? So I began with my Kakeya set here. I rescaled it to get this picture. And those blue guys that I drew were meant to be these global grains, which are the rescaling of these guys under this anisotropic rescaling. And I'm going to take one of them. They're all kind of the same. I'm going to consider its root rho neighborhood. And that is itself a tube, but I'm going to draw it as a rectangular prism. And that's this guy here. So I have several different complementary structures which are going to play off each other. And so one of them is I'm going to look at the global grains inside of this guy here. And there's going to be quite a few of them because remember, this sort of looks like a Cantor set. So you zoom in and rescale, and it looks like a self-similar copy of itself. And so these global grains, what I'm drawing here is just what's happening on the very bottom slice. But every single slice is going to have these grains. And I could draw what's happening on the top slice, and that's going to be a different set of global grains. And so each one of these lives in a Z equals fixed slice. And as Z varies, these things are twisting at roughly unit speed. But I also have these local grains, which are a little bit hard to draw, but it's what's going on in this picture here. And so the idea is if I look locally, let's say inside of a ball of size root rho, then I have these local grains, which are rho by root rho rectangular prisms. And they're all parallel to each other inside of each one of those balls of radius root rho. And as you move along these different balls of radius root rho, these grains are rotating this way. So they're twisting sideways. And you also have these global grains, which for each fixed Z value run the entire length of this slab. And as you increase Z, they're rotating this way. But there's a lot of consistency between these two different sets of objects. And as we're going to see, it's very, very hard for this consistency to happen. So here's what I want to do now. I want to compute what I'm going to call paths of length 3. And then I promise I'll finish. So I'm going to start at some point here. And I'm going to walk some distance along a global grain. How far am I going to walk? Maybe I'll call this distance y1. And when I get here, there's going to be a local grain, which allows me to walk upwards. So I'm going to walk upwards some distance, which maybe I'll call x2, along my local grain. And then I'm going to walk some distance along my global grain, which maybe I'll call y3. And then finally, I'm running out of colors here. Maybe I will write this as red. I'm going to walk back down to the bottom, and I'm going to return. And the point is that I'm remaining inside of the Kakeya set along this entire walk. Why is that? Because my Kakeya set is a union of local grains, and I'm walking along a local grain. It's also a union of global grains. I'm walking along a global grain. And if we do this carefully, then if for every amount y1 I can walk, and every amount x2, and every amount y3, and I always get back to some spot here, we can ask, what is my location here? Well, it's a little bit hard to write down, but essentially, there is a function, which maybe I'll call f, which is telling me how much I'm twisting as I move upwards. And there's a second function I'll call g, which is telling me how much I'm twisting this way as I go along this direction. And so what it looks like is y1, f of y1 minus y2, f of y2. It's not entirely obvious that this is what's happening. Dotted with, sorry, that should be y3, x2, g of x2. So I haven't told you what f and g are, but f is describing how my grains twist as you increase in z, and g is telling you how your local grains twist this way as you increase in x. And I start at this location here, and I want to compute what is my offset. After I've done this whole walk, I end up back somewhere here, which is offset from my original amount by some quantity. What is that quantity? Well, it's this guy right here. And what I want to do is I want to write this as capital F. Well, so I want to define capital F to be the graph of little f, and I want to define capital G to be the graph of little g. These are subsets of R2 now. And if for every choice of y1 and y3 and every choice of x2, I compute what's going on here, this is exactly f minus f dotted with g. And so what this says is, if I start here, what are all the possible offsets I can end up at? It's exactly, so here f is the graph of a certain function. In particular, it's a one-dimensional subset of R2. And g is the graph of a function, so it's a one-dimensional subset of R2. And I want to understand f minus f dotted with g. Those are all the possible offsets I could have arrived at. But I also know that this is supposed to resemble something like a Cantor set. It's an Alfors-David regular set. And so the question is it possible if I have a one-dimensional set f and a one-dimensional set g, and I look at f minus f dot g, can this be contained in a Alfors-David regular set, or is that impossible? And here's where we distinguish R from C. And then I promise a break. I apologize for going over. So here's my concrete question. Is it possible for f minus f dotted with g to be contained in a Alfors-David set? And an answer is yes, if f and g are orthogonal lines. Then f minus f is the same line, it's orthogonal to g, and the dot product is just a single point, and this can happen. Is this the only way? And over the reals, it's the only way it can happen. Over the complex numbers, there are other possibilities. So let's say f is x bar. Here, x ranges over all of the complex numbers. And g is, let's say, y bar y, as g ranges over all the complex numbers. F minus f is, again, all possible x bars. What is f minus f dotted with g? You can quickly convince yourself that every real number can be obtained in this way. So that's a situation where f minus f dotted with g, these are not orthogonal lines, but this dot product contains all of the reals, and the reals are a half-dimensional subset of C. And so over the complex numbers, new possibilities can occur. So there is this conjecture by Erdős and Volkmann that the only subrings, the only Borel subrings of the reals have either Hausdorff dimension 0 or they're all of the reals. This was proved by Edgar and Miller, and then a quantitative version proved by Bourgain. Bourgain's discretized sum product theorem. And that is lurking in the background and proving that the only way over the reals that this can happen is if f and g are orthogonal lines. It uses this Bourgain's discretized sum product theorem. What does it mean that f and g are orthogonal lines? It means that this function f at scale root delta looks linear. And that ultimately implies that globally your function f is C2. And this is really good. So there's more steps to be done, but we've essentially reduced the dimension of our Kakeya problem by 1. So our Kakeya problem lives in R3, but there's this C2 function just twisting as z increases, so that your entire Kakeya set looks like a union of lines pointing in that direction, given by a C2 function. And you can essentially project in that direction. So as z increases, your projection is twisting, but you have this twisting projection, which drops the dimension of your problem by 1. So you used to have lines in R3. Now you have, they're not quite lines, you have curves in R2. But we understand R2 so well that even if you replace lines by curves, we can still handle that situation and show that the union has to have full volume. So that's the final step. You reduce to a problem in the plane that looks a bit like Wolff's circular maximal function, for those of you that know what that is. And we understand that there are no counterexamples to Kakeya which come from Wolff's circular maximal function. Okay, I'll break there. So thank you very much.